I am Tamim Ahmed, and with my teammates Adnan Iqbal and Yash Sharma, we are presenting our term project for the vibration and noise control course. Our topic is vibrational analysis of a single cylinder IC engine with flywheel design. In this project, we explored the following key areas. We started with the basics of a single cylinder internal combustion engines, followed by theoretical background, calculations, and the methodology we used. We then carried out simulations using Python and MATLAB, discussed observation, and finally presented our conclusions. An internal combustion engine, especially the single cylinder type, includes several moving parts such as pistons, connecting rods, crankshaft, and a flywheel. Due to the cyclic nature of combustion and reciprocating motion of the pistons, such engines are particularly prone to unbalanced forces and speed variations. Understanding these dynamics is crucial in applications like automotive and aerospace, where performance, reliability, and noise control are key. The flywheel is a vital component designed to smooth out power delivery. It stores rotational energy and helps maintain uniform crankshaft speed by absorbing energy during the power stroke and releasing it during the other strokes. Apart from minimizing torsional vibration, it also assists in engine startup and contributes to overall mechanical balance. In single cylinder engines, the flywheel plays an especially important role in damping speed fluctuations. It is constructed using heavy disc-shaped component attached to the rear end of the crankshaft. The unbalanced forces in an engine arises mainly due to the inertia of reciprocating and rotating components. Primary unbalance comes from reciprocating parts moving at crankshaft speed, while the secondary unbalance is linked to the non-uniform piston motion, typically at twice the crankshaft speed. These forces lead to increased vibration, noise, and mechanical stress, issues that are more severe in single cylinder engines. Counterweights, balance shaft, and flywheels are common technique to mitigate these effects. And now I am going to present few mathematical relation between the connecting rod length, crankshaft, and the piston velocity. So as you can see, like r sine theta is equal to L sine phi, and therefore the distance between the piston and the origin can be written as S is equal to r cos theta plus L cos phi. So by rearranging, we can write it in this way: S is equal to r cos theta plus L into root over of 1 minus r square by L square sine square theta. For IC engine, we know that r by L is very less than L, that is denoted by lambda. Therefore r square by L square sine square theta is very less than 1. So after expanding, it becomes like this, and substituting sine square theta and sine 4 theta in this manner, we get the equation of S as r into cos theta plus 1 by lambda into 1 minus lambda square by 4 into 1 minus cos 2 theta minus lambda to the power 4 by 32 into 3 by 2 minus 2 cos 2 theta plus cos 4 theta by 2. As lambda is very less than 1, so S can be written in a similar fashion, and by substituting A0, A1 and A2, S is written like this. So the velocity of the piston can be derived by differentiating it. It's come out to be r into minus A1 sine theta minus 2A2 sine 2 theta into theta dot. So for the dynamical equivalence, we can write the three equation for the moment of mass. So in general, all the three conditions can't be satisfied by the two unknowns, that is MA and MB. By solving the first two, we can get MA and MB as follows: MA is equal to MC plus MC into B by L, and MB is equal to MC into A by L. And if we to find out the equation of motion, we carry out the moment of inertia equations, like we get the total kinetic energy as 1 by 2 I into theta dot square plus half ma r square theta dot square plus half m capital M into S dot square. And as we are neglecting any potential energy term, the Lagrangian become only the kinetic energy term. So the equation of the motion can can be as follows. So after solving all this equation, we get the equation of motion, and at steady state we can say that theta dot is equal to 0. And for the flywheel are attached at origin and connected with the output shaft. The moment of inertia of the flywheel is such that it follows these equations, and as kinetic coefficient of energy variation is difficult to calculate, we calculate the coefficient of speed variations. And for the good operations of certain machines, the coefficient of speed variations are as follows. For pumps it is 1 by 5 to 1 by 30. For machine tool it is 1 by 40 to 1 by 50, and for auto engine it is 1 by 200 to 1 by 300. For aero engines it 1 by 1000 to 1 by 2000. The methodology for our simulations: we model a simplified engine system considering both rotating and reciprocating mass effect, including a flywheel. To keep the model manageable, we assumed a sinusoidal combustion pressure and excluded valve timing and detailed combustion dynamics. Our goal was to isolate and study the influence of unbalanced forces on the engine vibration. Thank you.
Hello everyone, my name is Yash Sharma and I will be moving forward to present our work on the simulation of a single cylinder internal combustion engine using SolidWorks. So our objective was to model and visualize the dynamic operation of a basic IC engine assembly. So we begin by creating the essential components of the engine individually. These included the lower casing of the engine, the upper casing of the engine, the piston head, the crank rod, crankshaft, as well as the gudgeon pin. Now, each part was carefully designed based on standard dimensions and geometry to ensure compatibility during assembly. Now, once all parts were completed, we proceeded to the assembly phase in SolidWorks. So here we use the mate option to define relationship between components and simulate real mechanical constraint, ensuring that the parts behaved as they would in a physical engine. Special attention was given to aligning the piston crank mechanism correctly to allow for smooth rotational and translational motion. Now, as you can see, I will just show you that how this mate option works. I will select it, and then I'm going to show it by selecting this and this end. So as you can see that the crankshaft is aligned with the crank rod. In this way, you can do the complete assembly. Now after the successful assembly, we simulated the engine operation by rotating the crankshaft. And for that, I'm going to use the move component option that will allow me to move this crankshaft, and we will going to see the piston head motion. Now, as expected, the rotational motion should be transferred to this piston head, and the piston head should move up and down within the cylinder. So, as you can see, when I am rotating this crankshaft clockwise, the piston head is going up and down, as well as for anti-clockwise. So, this mimics the actual reciprocating motion in a real engine. We can also check for the piston head. If I am going to select the piston head and I will move it up and down, so as you can see, the crankshaft is rotating. So this simulation provided valuable insights into the mechanical interplay between different components and helped visualize how motion is transferred in an internal combustion engine setup. So moving forward with the code that we used for this IC engine simulation. So I have written this code in the Jupyter notebook and using Python and MATLAB to plot our graphs. So firstly, we will just put the engine configuration parameters, that is the bore diameter, stroke length, connecting rod length, the engine speed in RPM, reciprocating mass, rotating mass, the crank radius, and the number of engine cycles to simulate. After that, we will insert the flywheel configurations like flywheel inertia, the eccentric mass, and the eccentric distance from the center. Now for the simulation time configuration, we have taken a time step of 0.0001 seconds. That means after every time step of this value, we will record the values of the speed with flywheel and without flywheel and the unbalanced forces. After that, engine constants are defined and arrays are initialized to store the values of theta, speed when there is no flywheel, speed when there is flywheel, and the unbalanced forces. So in the simulation loop, for every I, we will calculate the unbalanced forces from reciprocating and eccentric masses. Then we will calculate the speed without flywheel, and then we will calculate the speed with the flywheel induced. After that, we will plot three figures in which we will show the engine speed comparison, that is, when there was flywheel and when there is no flywheel. Then we will show the unbalanced forces, that how they varies over the time with the crank angle. And then we can show the speed fluctuation, which shows the instantaneous speed difference, highlighting how much the flywheel reduced fluctuations. Now I'm just going to run this code. So as you can see, the three graphs shows up. The first one is the engine rotational speed over time, where the blue line shows the speed without flywheel and the orange line shows the engine rotational speed with the flywheel induced. Second one shows us the unbalanced force due to the engine components, that how it varies with the crank angle. And the third one shows us the speed fluctuation reduced by flywheel. So this modular structure makes it easy to adjust parameters, add damping, or extend to a new analysis such as force decomposition or frequency domain studies. Now my group member Adnan Iqbal will move forward with the observations made.
Hello everyone. My name is Adnan Iqbal and I'll be going ahead with analyzing the simulation results and all the observations that we obtained for different values of eccentric mass and eccentric distances. So, as you can see in those graphs, basically the behavior of unbalanced forces and engine speed fluctuations is measured by basically varying several parameters. So here we can also, get an idea of how the speed fluctuations influenced by the flywheel design, as you can see with all those orange graphs, orange plots in there. So we had basically four configurations, in which the first one was where we had eccentric mass equal to 0.015 kg, eccentric distance equal to 0.012. Further, we increased the eccentric mass in the second case 0.75 kg, in the third case it was 1 kg, and in the fourth case 1.5 kg. So with all those four configurations, we had plots which I'm gonna explain to you. So in the first plot, we basically uh, can see that the speed fluctuation with flywheel, it's not having that much of a fluctuation, and as you can see, it's almost a straight line. That means that in such a case, the speed fluctuations with flywheel doesn't have that much of a sensitivity. But as we can see, on increasing the eccentric mass to 0.75 kg, the fluctuations have increased and it's almost following a sinusoidal pattern, as you can see, and the amplitude of the speed fluctuation has increased. Also, you can see that in the first graph, the unbalanced force had an amplitude of about 2000, but in the second case, the unbalanced force is also increased upon increasing the eccentric mass and the eccentric distance to about 20,000 amplitude. Also, if you move further to the third and the fourth observations, on increasing the eccentric mass further, we can see that the speed fluctuations with the flywheel have increased to an even greater extent. And same goes for the unbalanced forces as well, which have increased even more. So, as you can see that this highlights to us that how sensitive the system is to eccentricity, and how basically without a flywheel or with inadequate flywheel mass, which is the eccentric mass, the unbalanced forces can cause sharp speed variations. So that is why the presence of a properly designed flywheel can effectively damp these speed fluctuations. And that makes me come to the conclusions. But before that, let me show you another observational graph that we obtained. So in this, the unbalanced force was divided into two components, the horizontal part and the vertical part, which had been plotted against the time. So these are two other graphs which you can see as well. These are also following the sinusoidal pattern, as you can see. So now coming to the conclusions are pretty much self-explanatory. So let me go around those. So basically the first point is that the flywheel significantly reduces the speed fluctuations. That was the whole point of conducting the simulation, where we got an idea of how important a properly designed flywheel is to control all the vibrations and control all the unbalanced forces present in an engine. So this model basically provides us a useful framework for analyzing and optimizing an engine performance by taking several cases of eccentric masses and eccentric distances for a flywheel. So that's why flywheel eccentricity is playing a critical role in contributing to unbalanced forces and dynamic behavior of an IC engine. And this simulation also helps us in highlighting the importance of balancing all the masses, such as the reciprocating and the rotating component masses, for the stability of an engine. And such models can help us in aiding the design of efficient engines with lower vibrations and improved lifespan. So that was pretty much it for basically our term project, in which we conducted simulations and showed you that how a flywheel is important in controlling the vibrations of an IC engine. So thank you to all for listening to our term project and our term project presentation.